Back on the desk, here we are, the follow-up looking at the GM AC Delco General Motors Model 61HFM3 LTspice simulation. It started with an old radio from the 1977 pickup truck. I rescued the volume in the tone pot. And out of curiosity, I wanted to know about the tone circuits in these old GM AC radios. I wanted to take a closer look at this circuit in particular because it had an interesting frequency response. There was a high frequency hump and there was a low frequency to high frequency trade-off, all centering around 1 kilohertz. Taking a deeper dive, I wanted to take a look at how does the loudness tap on the back of these volume controls, how does that work when I'm changing the level of the volume control here, and I'm also changing the tone control there. How do these two things interact? Because this is not a standard part. It's something that was very common in the old hi-fi systems. How do these things work? Okay, so I found this old Sam's Photofact on the internet, and it had a copy of all these circuits. I will leave a link to this in the description so you can download it for yourself, and you can take a look at this as well. This is the radio that looks very similar to the one that was in the truck and in the old Chevy that I drove around doing all my commutes in the 1980s and into the early 90s. Very quickly, we have a signal coming in from the amplifier. There's a branch that goes off to a balance control. Since this is a stereo, there's a pot up here and there's another identical looking branch that goes off to the other channel. Coming into here, there is a capacitor resistor that goes off to pull some high frequencies off to ground right at the start. Then we have this combination high pass filter and low pass filter going to either side of this 40K tone pot. This is a lot like the Big Muff tone control, where it also has this high pass and low pass filters that go to either side of the tone pot and then use the wiper to select how much of the high end or how much of the low end frequencies that you want. Where this one is different is that we have this loudness tap on the back of the volume pot. We come out of the volume pot and we have a low pass filter, ultimately going through a 1 microfarad cap where we go out to the power amp and ultimately to the speakers. Modeling this thing in LTspice, this is the original model that I came up with, where we have an AC signal going from 10 hertz up to 30 kilohertz. We have this high frequency roll off. We have the low pass and the high pass filters feeding into either side of the tone pot, which is modeled by 2 discrete resistors with some code that step through the various levels on the tone pot. And that feeds into the backside of the volume pot, which initially was just held statically in the center. So the loudness tap and the wiper of the volume control are each held there at the center. 10K on the bottom, 10K on the top. So this is a 20K volume pot. And then out through this low pass filter where we take our reading on the simulation. So the difficulty with the loudness tap is how do we model this long resistor here, the wiper, that's modeled like the tone control where we take 2 discrete resistors and then write some code to step through the values from minimum to maximum value. When I add this loudness tap on the back, I suddenly have 3 resistors to deal with. I have a resistor from the bottom lug to the loudness tap, from the loudness tap to the wiper, and from the wiper to the upper lug. To make matters more difficult, as the wiper moves past the loudness tap, then the position of these resistors is flipped. So what I wound up doing is modeling this whole contraption twice. First, we model the lower 10K on the pot. You can just ignore this 1 ohm resistor that I put there. The bottom half of the pot, I have my code here to step the wiper from its minimum position up to 10K. And there's my wiper, and I have a static 10K up on top. And then I ran another model for the upper portion of the pot. There's my 1K resistor there at the top. You can ignore that. I have my 10K on the volume pot on top, where I step the wiper from the center position up to the top. There's the wiper and a 10K static resistor on the bottom. Now in LTspice, there's not a way, not that I've found at least, to run both of these models concurrently and then have the output overlay on top of each other. So running the simulation twice, taking the output of each model and then overlaying them in post-production was how I came up with the slides that I'm going to go through next. So here's a screenshot with me running both simulations. Here on the left, I'm modeling the lower portion of the volume control. The output of those traces is up here. Then on the right, I'm modeling the upper portion of the volume control, and the output is here on the bottom. So the steps that I had to go through is running each of these simulations, taking the output, making sure that the vertical axes were the same. In my case, I would go from 0 dB down to minus 55 dB in steps of 5, making sure that was set for each one of these, turning off the plots for phase, and then exporting these as JPEG images and then combining them in PowerPoint, which is where all these things came from. So here's the first example of charts that are the lower and the upper portion of the volume control. This is 2 images that have been overlaid, and then the background has been set to transparent on the top image so we can see all the way through. We can see the lower curves and then the upper portion showing below that. This is why it was important to line up the vertical axes so everything would agree at this point. For the first run of simulations, this is my tone control down here. You can imagine it being held all the way up in the most clockwise direction. So this is 100% treble, and each one of these curves is a step along the volume control. And as we step through these, we'll start seeing the effect that loudness tap has when we change the volume. For example, here, from the lowest point on the volume control, right around this 1 kilohertz region, there is this hump in the higher frequencies. As the volume level goes up, we maintain this hump in the higher frequencies up to a certain point where the lower frequencies start coming in as well. Right about here in the minus 15 dB, that's where the wiper of the volume pot and the loudness tab are about equal placement on the carbon trace of the volume pot. Let's take a look at the next, where I've turned down the pot and I'm about 12 to 13% backed off that top level, about 88% of the way up. High frequency hump has come down a little bit as the volume control goes up, right around that 50% mark. I'm still looking at a pretty high amount of the high frequencies on the curves. And as the volume continues to come up, the lower frequencies start to add back in. On the next set, the tone control is backed off about 25%, so I'm about 75% all the way up, and we're starting to see a much more level frequency spectrum as the volume continues to come up. Right about the halfway mark, I'm at about minus 8 decibels overall, and we have a reasonably flat response curve up to about 5 kilohertz, and then we start to see some 3 dB roll-off. At the 50% mark, I'm just starting to perceive that the lower frequencies are the tiniest bit louder than the high frequencies. I still have this reasonably flat frequency response. There is a slight notch around the 1 kilohertz range, and there is a little bit of a hump still in these high frequencies. But now as the volume continues to come up, that characteristic hump has gone away, and the lower frequencies are starting to be slightly louder all the way up to the upper regions of the volume control. Continuing to turn the tone control counterclockwise. I'm at about the 25% level, or 75% turned down. There's the same characteristic flat response across the bass frequencies, a little notch at 1 kilohertz, a slight hump for the higher frequencies between 5 kilohertz and 10 kilohertz. As the volume control goes up, that characteristic slant in the frequency response just continues to get louder. Something interesting starts to happen here at around the 50% volume level. There is a little bit more of a spread in this mid-range. So the effect is, as I'm turning the volume up around that halfway position, the middle and upper frequencies are starting to have a little bit more gain or less attenuation. So we're starting to see the effect that the loudness tap has at around that 50% volume and about 25% over towards the bass frequencies. With the tone control at about the 9 o'clock position, that puts me 87.5% towards the bass. We can see that the lower frequencies, when the volume is low, the lower frequencies are more present coming through the volume. And as the volume control goes up, the upper and lower frequencies are in lockstep up to about the halfway point where the wiper meets the loudness tap. And there's this characteristic spread that happens again at around that 5 kilohertz region. And as we continue to turn up the volume, those upper mids and higher frequencies are less and less attenuated until we have a flat frequency response in the upper levels of the volume. In this last chart, the tone is all the way counterclockwise, so we're in the most bass setting. At the lower volumes, frequencies above 1 kilohertz or so are attenuated. And as the volume goes up, it pretty much maintains this same high frequency roll-off that I would expect up until about the halfway point where this characteristic spread around 5 kilohertz starts to happen again, and the upper mids and higher frequencies are less and less attenuated as the volume control continues to turn up. So it's very curious, and I must admit, the loudness tap didn't behave like the way that I read about online. It's not that it particularly favored low frequencies over the upper frequencies. It has more to do with if I'm in a bass favoring setting on the tone control, the upper frequencies really don't come into play until I'm at the position of that 50% mark. When the wiper meets the loudness tap, then those frequencies are allowed through more. When the tone control was at the high frequency favoring position, moving the volume control tended to favor those upper frequencies up until about that midway position again. So as the wiper comes close to the loudness tap, things begin to level off and behave more or less equally. So the loudness tap favors the frequencies that are set on the tone control, not just the lower frequencies. Now, I have read a few people suggest, and I have thought the same thing, that when we're trying to repair these kinds of volume controls with the loudness tap, the first thought that comes to mind is, well, what if I just took some static resistors at these opposite lugs and just ran some resistors on the outside of the pot to create a virtual loudness tap? And the response is usually, well, it doesn't work that way. But no one has ever shown any evidence of what does that actually do. Since I have a model here and I can do these kinds of things, let's do just that. Let's model the volume pot as a common potentiometer with just my two resistance values to worry about. I can step through those easily enough. But now I've got these static resistors at 10K each to create this virtual loudness tap. What would that look like? Now, I know someone's going to watch this and say, well, hey, Bill, we've got a 20K volume pot, and when you add two 10K resistors like this, you're creating a parallel path, and everything, you should double everything. So I should have a 40K volume pot and two 20K resistors here to keep everything in line. Well, I tried that. I also did a simulation with that, and it really doesn't matter. It has the same effect, and that effect is it still doesn't work. Let me show you what happens when I run this simulation. Fortunately, this simulation is a lot easier because I can model both the volume and the tone control in the same simulation. I don't have to overlay graphics like I've done before. So stepping through the volume and stepping through the tone controls, I have a 20K volume pot and a 40K tone pot. And what we're seeing here are these clusters of curves for each of the steps in that volume control. And that fuzzy cluster of lines that are all collected here, that is every position on the tone control. So you've in a sense defeated the entire purpose of the tone control here, and all you're doing is you're just having some filtered signals come in to the volume pot. It really doesn't work. You maintain the same slightly bass frequency favoring tilt, and it goes up in volume as I change the volume pot. This is a radically different set of curves to the bass favoring and high frequency favoring curves with the loudness tab. Wow. So having taken a look at all of that, this AC Delco volume and tone control, the effect that the loudness tab has, I didn't know what to expect, but that's not what I expected to see at all. The way I understand how a loudness tab works now, it's basically a second entry point into a potentiometer. I have that uppermost lug. I've got the resistors that the wiper passes over. So I have a voltage divider from the maximum volume down to some setting in between there. But the loudness tab acts as a second entry point. So you can think of it as it's a voltage divider that has two inputs. And as the wiper comes down and passes the loudness tab, now I've got this combined equation where we know what the equation is for a normal voltage divider. And when we've added that second input, it adds another term. So now I've got a voltage in 1 at the top. I have a voltage in 2 in that center position. And then I can add these two fractions to get an output volume. So now I'm starting to understand how the tone control works. And when it comes in that second input, now depending on where the wiper is, it changes the way that that ratio reacts, because that second input has a different response in the ratio as the wiper goes past it. I'll put the equation up here and you guys can have some fun and telling me where it's wrong, or if it's close to being right, you can have some fun determining, how it gets response curves like this. I have not seen any other analysis on this kind of stuff online. There's a lot of thoughts and a lot of conjecture about how it might work, but this is some quick analysis using a tool that I'm not a professional in any way, shape, or form, but it's out there now, so you guys can take a look at it and throw darts at it and poke holes in the theories and all that kind of stuff. That's fine. I've got no problem with that. But anyway, putting my I'm just a guitarist hat back on, the project that I'm trying to do now is I'm rebuilding that tone and volume control circuit in this device because I want to know radio volume and tone controls are fine, but what does it sound like in a guitar amp? And that's where I'm going with this stuff next. I've already got my volume control in here. I'm waiting on the appropriate value tone pot to come in so I can finish kludging this circuit together, and I can put it on the test amp over here. We can have a listen to it and see, it may be cool on a radio, but does it work in a guitar amp? And that's really what I want to know about, because I've got bigger plans for this if it works or not. If it doesn't work, okay, I've spent a lot of time doing some analysis and I know to not continue. But if it does sound cool, I'm going to have a pretty bitchin' guitar amp come out of this. If you're digging this kind of stuff, I encourage you to subscribe to the channel so you can follow that stuff when it comes out. All right, check you guys later.